third time that I've been in one of your classes.
Yes.
I'll get it on record, you're pretty good.
You were in my PhD class, right?
CFD, and I thought that
I think I graded one of your classes. You made me, I think it's.
you were the TA or.
Yes,
in
fluids
the
or
class.
solids, I did solids.
Solids, that's what it was. And here, cool.
Actually, we don't have a lot to discuss here.
Yes, pretty good.
But I just want to summarize what we did in the class. So just to keep up with, okay, first of all, we need to just read this a little bit. Nathan, you got this one, right?
Yes, sir, I got it.
Okay. You Matthew, right? You Matthew? And you Prince? You was Hey.
Wow, you're good at this class.
He's had to put up with this for a while.
Okay, so what are the measurements that we have to take? You can, he pointed out some of the measurements in the handout. And I would advise you to read the handout very carefully because I noticed when I'm grading the last report for your assignment, there was one hint that he has provided when you're doing problem number 2 or 3, that if your S value goes below 1, you have to assume that S is equal to 1.
I would have still.
Yeah.
Right?
I wonder if I changed that.
That was in the handout, but most of the students missed it somewhere.
Oh, really?
So be careful to read the handout, okay? So,
Yeah, because then you end up with just 1.96, I think it was.
yes,
It was
1.96, and then again he take it to 2 because that instrument has only precision up to 1 psi.
Yeah.
So you cannot go beyond that.
So it would have either been 1 or 2.
Yeah, your measurement shouldn't be precise than that.
I just remember multiplying one.
Yeah, but when you take the voltage measurement, you can because it has 4 decimal places. So,
1.96 with the Z factor calculated, though, right?
Well, when you're calculating your uncertainty, though, you.
yes, it's not that. Not that.
Because it's like-
I'm talking about S value, that's the standard deviation. You
Yeah.
find the standard deviation, right? When you find the standard deviation, if the standard deviation is below your least count, then you assume that your standard deviation is 1 because it's a least count.
Yeah, and if
You
it's-
cannot measure more precise than the least count.
So if it was like 1.03, our calculation, we'd automatically have to bump that up to 2 because.
Not really. In that case, you can take
Close
1.03.
enough.
Yes.
Okay. I remember, we said that.
Okay, guys, now
Yeah, and I figured we should.
Today,
In my mind.
we have the orifice plate is one of the measuring devices, the flow rate measuring devices. We have the same kind of measuring devices called nozzles and venturidiums. And we have these orifice meters. And all of these work on the same principle, right? If I draw a schematic, like this. Now this is the upstream of the flow. This is the downstream. So when the flow comes here, since due to this sudden contraction, the flow tends to neck down like this, and it creates some swirling here. And then it comes in the same shape. So the diameter of this pipe taken as D, and the orifice diameter is D, small d. Now, I think probably you have derived the equation in the class, right? By using the Bernoulli's principle and the mass conservation. So how do you write the Bernoulli-Weinberg? What are the components you have in the Bernoulli equation?
The, Q actual.
No, I'm not. I'm asking what is the
components.
Bernoulli's equation?
Pressure, volume.
Yeah.
Pressure plus
1/2 rho V squared.
1/2 rho v squared plus did you mention the other one?
Yes. It's well, that would be P1 on that side.
That's right. I need only one side. It's going to be equal to a constant. So if you take a streamline, you can apply this equation on a streamline. Right? There are certain conditions that applies that allows you to apply this equation. The flow should be in some condition. What are those conditions? Do you remember that? Flow should be what?
Laminar. What's that one?
Well, in this case, actually we consider flow is inviscous,
Oh, yeah.
right? So viscosity is 0. Now, if the flow is going to be laminar, then it's viscous flow,
Right.
right?
Yes.
So if the flow is inviscous, this theory applies on the inviscous flow, not the viscosity. If the viscosity is there, what would happen?
Well, you got
Energy,
friction.
friction. What the friction is?
Because we didn't compensate this as ideal, so don't we need like a correction factor?
Yeah, we might need some correction factor. You might have applied that in when you're doing pipe flow problems in fluid mechanics.
Yes.
You had the friction loss, which is called edge loss, right? But here we don't take that into account. So we simply think it's in viscous flow,
Okay.
right? And what about you think about the density?
We're assuming it's constant.
It's constant. So what is the density constant flow is called? What do you call that kind of flow? Or fluid? There's a word that you use.
Density is constant?
No.
No, but I mean, that's what you're asking, like what kind of flow for constant density?
No, there's a name that is given in fluid mechanics for a constant density flow.
Wouldn't it be fully developed? Like,
Have you heard about any name like incompressible?
Oh, yeah.
Okay.
My brain is moving slow.
Yeah.
That means if the bulk modulus of the flow is very large, or pressure differences doesn't affect much significantly. Okay, so that's called flow is incompressible. So flow is incompressible, and you have another term that is gravity. If you say, now this is horizontal pipe, so we don't have to care about the gravity if you apply on the streamline, right? But if you have a flow like this on a pipe, now you have that gravity component because you measure the distance from a datum, so you have gravity component, right? So you have pressure here, and this is called the pressure and kinetic energy. This is the potential energy.
Yeah.
Okay, so this is an energy conservation equation in other way. Right? Well, this equation is an energy conservation equation. Now you use that equation for two locations here as 1 and somewhere here as 2. Two locations. And he used, what is the other equation that he used to derive that?
The beta, or where you use beta to.
No, that is a simplification, I guess. What else?
The three things that I remember that we covered was mass conservation, Bernoulli equation.
What's the first one you say?
The mass conservation.
Mass conservation. Okay, you have mass conservation, that is m1 naught is equal to m2 naught.
Right.
So if you express the mass in terms of velocity and area, what should be that?
Pi over 4d squared.
Yes, you have rho 1 pi over 4 d squared is equal to rho 2 pi over 4 d squared times the velocity, right? V1 and V2. Now, since the flow is incompressible, you can get rid of this density and you can simply avoid these two terms and you will get some now we're going to find V2, right? So you can express V1 in terms of V2, right? V1 is equal to d squared over 3d squared times V2. Then you substitute that into this equation and obtain, I'm not going to derive that equation, okay? Because it has been already derived. So you get Q, the flow rate, is equal to C of D, that is the discharge coefficient, times 2 times P1 minus P2 divided by rho times 1 minus beta to the power 4. Now we're going to end up with an equation like this after you solve these two equations, right? You have to apply Bernoulli's equation for 2 points and then solve from this equation. And beta, now beta is another term, beta is equal to now, I initially said that we use orifice meters to measure the flow rate. Now, flow rate is a function of coefficient of discharge times this. Now, we have to measure some things. What are we have to measure to find the flow rate?
Pressure difference.
Pressure difference. How do you measure the pressure difference?
Using the manometers.
You can use simply manometers. Very good. You can use manometers. You can put the manometer probe here and then somewhere here, and then use the difference of the fluid levels, right? And then you can take the pressure difference. Do we have to take this in terms of absolute pressures or not? Or isn't there any difference?
Could be, it doesn't matter,
It doesn't matter. Why?
because it's gonna be the same difference regardless of whether we compensate for.
Yes, that's right, absolutely right, because atmospheric pressure is constant at that location, so on that particular time, right? So it doesn't matter whether you take absolute pressure or not. So simply if you have the fluid level differences of the manometer, if it's the fluid manometer, then you can take the pressure difference. Now, in this experiment, we need to measure the pressure difference and we need to measure the two diameters. In the pipe diameter, I will show what you're going to measure. And then we have to calculate the flow rate, but we don't know what is CD. To find CD, we have to use another instrument. So the aim of this experiment is kind of calibrating this orifice meter. That means you find that CD for the particular orifice meter. Because you can change the size of the orifice. You can have a smaller d or bigger d for that small d, right? You can have a smaller plate with a small orifice or big orifice.
Does this one have a stamped value on it that we're going to compare to what we calculate, or?
Which value? Oh, there's the Q flow rate or CD? No, you don't have a standard value. You have different plates, right? You can
And
choose.
for each one, like they don't have their own, like they're not tested and then stamped with.
No, it's not, they are not stamped. As long as I know, it's
Well,
not
it would
stamped.
change though
Yeah.
too, based on temperature.
Yeah, based on the conditions on the day, it might change.
I just didn't know if there was a standard, like if this flow rate and this conditions, this is what you should get. Like some kind of, something that you could compare to if you were to test like an experiment.
Yeah, that's a good idea.
Because then you know how close or far you are from an accepted standardized value.
Well, we did an experiment before we start this class last week. So
Well, that's kind of what I'm talking about.
yes, so Mr. Moser has the data, and he
Okay.
might not calculate it, but
Okay, well, that's good.
Yeah.
So that way, like, you know that we're at least on the right track or way
Yeah.
off. Or, all right.
that's right. That's why we do all the experiment like a week before
Okay.
for the class. So Then we have all there.
See, this is,
Okay, so now we need to calibrate that. That means find your CD, but we don't know what is Q. We have to know Q. Now, how do we find Q? How do we find Q?
when you do the area by velocity, I don't know.
Well, if we know our mass flow, we can find our volumetric flow.
Right, we know the mass flow rate. How do you calculate the mass flow rate? That's another important thing. Now in this through this pipe system, air flows through. Right, so if it is water, you could have calculated, you can put a bucket at the outlet and you can measure the amount of volume and you can record the time. Then you can have some kind of flow rate value, right?
So,
But now, at air, you cannot collect like that.
so we'll be using like what, fan or turbine, so.
So you think that it has a nominal flow rate?
Yeah, like depending on how
Fast
much
it
you
moves.
turn it up, yeah, like what.
Yeah, that's one possibility. That's one possibility, a good one. But here we have a separate flow element. That's called laminar flow element. It looks like this, and actually one of these is connected to the system, right? So it has right here. If you look at the actual one here, that's the same one. It has some flow rate in cubic foot per minute. Okay. So at nominal temperature and pressure. At nominal temperature and pressure, it has some value for flow rate, right? So, but when you do the experiment, your temperature and pressure on that day might change. So you need a correction,
Yeah.
right? For a laminar flow, flow rate can be expressed as Q. Some geometrical constant C, okay, divided by mu times delta. Okay, let's say this is standard flow rate, and this is standard mu. What is mu?
Viscosity.
Viscosity. So viscosity changes with the temperature, right? So you need a correction. So if you say that the actual flow rate of the flow QF is equal to, again, see these are geometric constant, those doesn't change, but your mu changes for the same delta P. For the same pressure difference, okay?
So are we gonna do like checking what the pressure is in the room again, what the temperature is, and then calculating viscosity?
Yes. You calculate the temperature. Now you have to measure the temperature at the two locations, T in and T out of the laminar flow element, right? Laminar flow element. And then you average the temperatures. So you find mu f at the average temperature value. So what are the measurements that we have to take? The pressure difference and temperatures, and you have to measure diameters, okay? And what about this?
Calculate
Rho is calculated. How do you calculate rho?
what we did.
Ideal gas flow. Very good. Now to calculate the rho by using ideal gas flow, what else you require? Now ideal gas flow is PV equals MRT, right? And you can take it, rho is equal to P divided by RT, right? And you need pressure, gas constant, temperature. Now temperature is what? Ambient temperature.
Yeah.
R is a constant, you know that. What is P?
Absolute.
Yeah, wouldn't that be like your barometric, like what we did?
Yes. You have to find the absolute pressure. Okay? So you need absolute pressure for that. Fine. Okay, so you have to take the barometer reading as well. So those are the measurements that you can take. You have to take the pressure difference across the laminar fluid element, the pressure difference across the orifice meter, and you take the pressure difference across the fan, because that pressure is required to calculate rho, because that's the rho you have in that condition, not the atmospheric pressure, but the pressure built up by the fan. Because pressure is built inside the pipe system than the outside atmospheric pressure. It's a higher pressure. Okay? So you take that pressure. So you need to have 3 manometers basically, right? In the system. Now when you go there, you can see it. And then you have 2 temperature gauges to measure the temperature here. And you have to take that temperature measurement there and the barometric reading. Okay? That makes sense? Alright, we can go to the.
I got one question.
Yes.
For the pressure and the temperature, it shows to only take one reading, but if we wanted to determine the uncertainty, standard deviation, and everything, wouldn't we all take that measurement?
No. Well, you can get the single measurement.
Single sample.
Yeah, single sample measurement. So,
Which is easier.
1/2 your piece.
yes. But your error increases.
Yeah.
You know that those things right now, right? Because you
Yeah.
did.
Well, I think he told us too, though, in the slides, he gave us some of the values for the uncertainty based on
Yeah, we're going to use them.
previous slide.
Yeah, but we're going to use the uncertainties based on what we've already calculated.
Yeah,
Okay.
because he averaged them all from all processes, so it's like 0.003.
So Nathan basically is going to take this data and do the report, right? Is that what you're going to do? Or the previous data?
No, I'm with this group.
Okay.
I've already
That's cool.
scratched
All right.
that.
So you let others know that you changed the group, the other group members?
Yes, I listened. We were all on
Okay.
drop off. I sent them all the message.
Okay. Any other questions, guys? No? Let's move on then. You can see this one. This is filled with very tiny holes. And I don't know if you can see the light through this.
Can we use it as a flame arrestor?
You can see some kind of light, but I'm not sure. I think it's this light or the reflection.
It'd be the biggest one you could ever have.
You can see through it. You just have to blow it out a little bit.
Well, you can make a laminar flow if you have straws.
Yeah.
You can bundle up straws and put it in a single pipe. I had one undergraduate student when I'm teaching in Sri Lanka. He made a laminar. It's called water fountain or something like that. It was a laminar tube. It was like shoots up the laminar fluid layer of tube from the jet of the pipe. He actually used straws. One of straws. Okay, guys, these are the policies. You can pick whatever the one you do. Okay? Well, there are different sizes of those. You can pick whatever you want. And then what you have is to measure the inside diameter. Okay? Take one you like.
We'll all measure.
What do you think about the air? Now you have to measure the diameter, right? So that will carry some error for the experiment, right? So what do you think about the error according to the size of this orifice? How the error propagation behaves depends on the size of the orifice. Remember?
Yeah, I don't know what you
Okay, yes.
I didn't fully understand it until you told me that.
Like, well, when do you measure it? How does it sit? Like this?
Okay, now that's the question again that I need to ask. Which side should be in the upstream side? When you
Well, the way you drew it, then it
So that's the upstream side, right? So the flow comes in this apparatus from here to there. So this is the upstream, this is downstream. So your bevel side should be facing the downstream.
Yeah.
Okay.
Okay.
So that's good. Now, which one you pick? And my first question, you didn't answer that.
I don't know if I know
Which one?
Okay, which one has the greatest error propagation according to the size of the orifice? Now you have to take a inside diameter. Now when you measure inside diameter, it will carry an error. Which error would be significant for the final result? I'm asking if you use a smaller one
Yeah.
or bigger one.
I understand.
Or significance, okay, I will let you do. Significance of the error is important when the measurement is larger or smaller.
I was thinking it's smaller, but I guess larger is pretty good.
What?
So I was thinking smaller at first, but
It has more error.
only because like it's tough to be accurate. It depends what you're measuring with. The smaller you get, it's harder to be more accurate with your measuring.
That's right. That's right. Okay. So if you use a bigger one, you get less error percentage because if you use smaller one, because we're going to use the same instrument to measure, and it has same least count.
Yeah.
So
It matters a lot more.
yeah, this matters a lot more. It doesn't matter whether you like a small one, you can pick a small one or bigger one and pick your as you want and then measure it.
Go with the big one, though, more accurate. It's the Chinese one too.
Okay, guys, use this.
So
Calipers?
each one of us has to measure.
Each one of us you have to measure that, and we'll set up the computer, and then you guys have to measure the inside diameter of this big pipe. But you cannot measure right here. You have a same pipe over there, so you can measure it. One of you can measure that, and the other one can measure the other one. Okay?
Can I use these to take a measurement? So y'all okay with that?
I'm fine with it.
It's gonna be more accurate.
It's going to be more accurate, but
You want us to see which causes the error, right? Because out of the 7.
well, you can measure it, but you have to use that one and measure it. Yes. Yes, for the experiment you can use that one, but it's good to use this one to practice. You can also practice what is standard. Yes, yes,
Yeah.
yes. Yes. Okay, guys, can you, okay, this one, you have to close the doors and see whether it is, this value is achieved. Okay? If not, this one can be looked at and tell me. Okay? And then, when you take the measurement, if you want to lock the doors, you can lock the doors. Guys, did you check for the initial error? Did you check for the initial error? Check it. Close this close and see whether this value is at 0. If not, okay, close this screw. Close this one and turn the dial. Okay? Because the screw doesn't adjust the dial is adjusted. So make it 0 first and then. Huh?
It's just a fine adjustment.
No. It's for locking the measurement. If you have, let's say you want to take it out.
That's all.
Yeah. Okay.
Used to be other ones better.
Group 1.15.
like,